So I would also like to thank the organizer for this nice conference and kind invitation. So as usual, it's always good to come back here. I will be talking about many-body localization, and in particular, I will be talking about dynamics in the many-body localized phase. And I will try to show you that the dynamical properties, even though initially you may think that the localized phase is very boring, but there are certain interesting aspects in it as well. The most of the thing I will talk about is in this recent work, and some of it is in preparation. Okay, so let me start with the setting. So the setting is as usual. So in usually the experiment that we will be talking about is a cold atom experiment or ion trap. So it's a 1D system. We'll be talking about 1D system where particles are hopping in a potential which is disordered site to site. So that's the usual setting that we will be talking about, and without any interaction. So we have a many particle system. Without any interaction in the system, the single particle eigenstates are exponentially localized in space. Okay, so that's the basic idea of Anderson localization in 1D. So all my talk will be about 1D and many particles in the presence of interaction and disorder. Good. So that's kind of a cartoon picture, if you wish. So the single particle eigenstates are localized within some localization volume. We'll call it xi, and that number will become important, and we'll come back to it many times. Okay, so in this context, the question of many-body localization is the following: that what happens to this system when you turn on interaction between those particles, whether the system remains stable, remain localized, or something else happens. So what we need to think about is the following: that here I will be talking about a little bit different space. Instead of a real space, we will be talking about many-body Fock space now. And in this Fock space, all these single particle eigenstates are forming Slater determinants without any interaction. So think about it as a space of Slater determinants, where all these Slater determinants are essentially localized. So this is kind of a graph structure, if you wish. So that's your first part of the Hamiltonian. Now what you add is the interaction. So it's a 4-fermion term, which is like this, where V, alpha, beta, gamma, delta are the matrix elements, which is constructed out of the single particle localized eigenstates. Okay, so what it gives is in this many-body Fock space is the following: that the interactions allow you to hop from one Slater determinant to the another Slater determinant through the matrix element V, alpha, beta, gamma, delta. Okay, so naively one would expect that through this hopping, eventually the particle will delocalize, and that's essentially the decoherence mechanism, and no localization will survive. So that's kind of the common and general picture. However, these are the two seminal work almost now 13, 14 years back, which where they said that if you think about in this many-body Fock space, there can be a regime where you will see that the particle is not completely delocalized, but there is a regime where it is localized, and I will tell you in which sense it is localized and so on and so forth. So two important things that I will be mostly interested in, that I will not be talking about phonons. So there is no path that is attached to the system. Therefore, the system is completely closed. Okay, so therefore, the notion of temperature will be replaced by energy density. So that's the only slight difference that I will be talking about. So the basic mechanism is again very simple. So we can think about in the real space, and this xi again comes back. So this xi is, as you realize, is the localization volume where a single particle resides. And the interaction allow you to hop from one volume to another volume, as the matrix elements I showed you. And the basic process, the basic inelastic process is the following: that the electron-electron interaction gives rise to electron-hole pairs. Okay, so a particle hops from one localization volume to another localization volume, generate two electron-hole pairs, and it keeps on going, doing that. And through this, you are essentially creating many particle-hole pairs, and as this dephasing mechanism that I was mentioning previously will allow you to delocalize the system. So essentially hop through the system. However, as I said, it doesn't happen like that. And one simple way to visualize is the following thing that I always show. So what I plot here is essentially the return probability. Think about a system, 1D system, where you have initially have some initial density of particle, and you ask over time what happened to that density of particle. Okay, so please look at as a function of time. And return probability just means how much particle density survives in the middle of the sites or wherever you put the initial density. So this is one particular disorder configuration, particular sample, where you look at some disorder values 1.53. I'll make it more clear what these W's and V's are. But essentially some weak disorder and strong disorder, no interaction, And what you see is this solid line which just goes back and forth and back and forth and back and forth. So this is essentially some oscillations, and these oscillations are signature of localization, if you wish. So you have a localization volume xi, where the initial particle density was, and it cannot escape that box, if you wish. So therefore, this is doing sloshing back and forth some oscillations. So this is these oscillations that you will see, and this is what is called mesoscopic fluctuations of a sample. Now, on that thing, you turn on the interaction. So V is the strength of the interaction, if you wish. You turn on the interaction, and what you see is the following, that immediately, so these are the dashed line, immediately this fluctuation wash out. The other way of saying this coherent oscillations that you are seeing is just gone. Yeah? And that's a signature already that tells you that the fact that the particle or the density of particle was sloshing back and forth is lost. Somehow it kind of decays down. And this is indeed what you see at weak disorder. There is a kind of a tendency of flow that the mean thing, the mean density goes down to 0. If you wait long enough, that thing goes to 0. But MBL is, as usual, is not like that. So this is very strange, and this is the most unique feature of MBL. So even though the oscillations are gone, but still the initial density is very high. Okay. So other way of saying, even though the coherent oscillation that we are seeing is destroyed by incoherent mechanism, which is this electron hole pair, creation of electron hole pair, but still there is a perfect possibility to have a localization even in this interacting system. Again, so this is done at very high temperature, or in this closed system we will talk about energy density. So at very high energy density we are talking about, or in technical terms we call it infinite temperature. Good. So that's MBL. So the oscillations are gone, but still there is a finite density of states, a finite density of in particles. So more or less other features also emerges in this localized phase. So one of the very interesting feature is the entanglement entropy, or what you call it bipartite entanglement entropy or half chain entanglement entropy. And you start with an initial product states where the initial state has no entanglement entropy. But over time, what happens that if you, so this is some again measure of interaction, at zero interaction there is an initial growth. Again, the growth of the initial state is just within the localization volume. So if you wish, that's saturation, and then it saturates. So this is essentially the localization volume of the non-interacting system. But then you turn on even a very small interaction, and what you see is that initially it follows the non-interacting curve, but then eventually it grows and gives entanglement growth, and that is logarithmic in time. Not only that, it's at what time it grows is proportional to the strength of the interaction. So as you increase the strength of the interaction, it takes shorter time to grow entanglement growth. Good, and indeed that's what happens. So if you rescale the x-axis with the interaction strength, you see that there is a collapse in the curve, which just tells you that the interaction or the time scale that it takes to grow from the non-interacting value is essentially proportional to the interactions. So now one can go to very long time, and what can show that where this entanglement saturates. So this entanglement entropy saturates at some value, for these are some different system sizes, and that value essentially grows in proportional to L. So after the quench, so this is a quench experiment, after the quench there is a volume law entanglement entropy of the state of the final state. So which also says that it kind of spans the Hilbert. Whereas for the non-interacting case, there is no growth whatsoever, so it just saturates. So that's another key difference between an MBL, which is an interacting localized system, instead of a non-interacting localized system. Good. So many things we know by now about this MBL system. So for instance, this is a kind of a phase diagram which is plotted as a function of energy density. Again, temperature has been replaced by energy density as a function of disorder strength. So this is kind of a cartoon picture. And what we know that there is a difference in phases. So by tuning the strength of the disorder for a given interaction strength, we can go from an ergodic phase to a many-body insulator phase. So by ergodic phase, I mean that it obeys ETH or eigenstate thermalization hypothesis, whereas in the many-body insulator that doesn't happen. So one of the key features of these two phases, distinguished phases, is that there is a transport. So there is a finite transport or sigma dc. So if you calculate conductivity at zero frequency, you will have a finite value over there, whereas in the many-body insulator, there is no transport. So that's the most distinguished feature. From the entanglement point of view, this is an eigenstate phase transition. What it implies is that if I calculate eigenstate entanglement or bipartite entanglement, it will be a volume law, goes to an area law entanglement. From the thermalization point of view, it will be an ETH. There will be no ETH, and on top of that also there is some kind of a Wigner-Dyson level statistics which happens in a chaotic system or in the eigenenergies. And also there is this type of transition that happens while we talk about MBL transition. Good. So the most important feature that I want to point out is the fact that if you sit at a given disorder and you move up in the energy density or in an open system as a function of temperature, what you see that even at a particular disorder, you go from a localized states to the anergodic state, and this is what is called mobility age or many body mobility age. So that's the finite temperature phase transition that is the most important thing over here. So this is all what I have been talking about is 1D. This feature is 1D. Everything is 1D, 2D is not known, not clear. Good. So what I want to talk about, let me be more specific. So I will be talking about this particular Hamiltonian. So this is essentially a spinless Hubbard model or XXZ model. So I have a nearest neighbor hopping, the C fermions. Then there is a potential term. So in particular, I will be talking about a potential which is not fully random, it's a quasi-random potential. So this is called Aubrey-Andre potential, where it's almost cosine except that sigma. The sigma is an irrational number, which is, in this case, golden ratio. And then there is a interaction which is nearest neighbor interaction. And what I will be looking at is a density-density correlation function at 2 time and 2 point. So this is a density-density. So this is my density, Ci dagger Ci. And this is a connected correlator. So why I am interested in that, because this is essentially, if you think about a little bit, so density is related to current correlator, which is in terms related to the sigma or the conductivity. So at the end, I want to know whether there is a transport or no transport, because that's the distinguishing feature between an MBL and non-MBL. And in precise, I will be looking at delta x. Delta x is essentially the second moment of this correlation function. Okay, so in other words, we will call it a transport distance. Good. So what I will show you is the following. So I will just focus on the localized phase, not in the ergodic phase, and I will show you an interesting feature already. So this is this delta x that I plotted. So this is the delta x as a function of time. So this is an exact numerical simulation for different system sizes. And the first thing that you note is the v equal to 0 part. So in the non-interacting case, this is a localized system. Therefore, there will be no transport whatsoever. In these terms of delta x, what it means that it will saturate. Yeah, so it cannot go beyond the localization length. Therefore, this delta x is going to be a saturated function, which is what you see. However, even though the disorder strength is quite high, so this TH is the hopping strength, and the interaction is, in this particular 2 cases, is 2. In these cases, the disorder is quite high, and we believe that with the other indicators of localization, this system is localized, but this delta x keeps growing. Yeah? So it's not a power law growth, but it still shows some growth of the particle distance, if you wish. The other way of saying that even though the entanglement, the other kind of measures will show that this phase is localized, but the distance between 2 particles or distance between densities keeps growing. It doesn't grow as a power law, because if it is power law, then it would be diffusion. Diffusion tells you that this is the sigma dc will be finite, but here it is not the case. It's logarithmically slow even, but still there is some interesting feature that goes on. Okay. And this is not only the numerics that shows this. So this is a very recent experiment from the Marcus Greiner group, where they did a cold atom experiment with 12 sites, and what they show is precisely exactly this quantity, transport distance, as a function of time. And they have 3 different regimes. So thermal regime is essentially the ergodic regime, where it's supposed to go very fast and then it saturates to the thermal value. Then there is a critical regime, which is the close to exactly, by the way, this is also the same potential and so on and so forth, except they don't have a fermion, they have a Bose-Hubbard model, but that's almost similar. And in the critical regime, there is also growth, but also in the MBL regime, which is in this unit 8.9, also there is a little bit of a growth. And indeed, they characterize all these exponents, so by looking at these power laws and as a function of disorder strength, and what you see that there is a decay of this exponent, but even at very deep in the MBL phase, the particles are moving. It's not that there is no movement of the particle in this system, which is unlikely the Anderson case, where Anderson case will have no movement at all, and this alpha will be 0. Okay, so why so? The idea here is the following, that we have kind of a 1/L correction. So this is kind of a, if you wish, a quantum phase diagram or the critical point diagram, where usually for the quantum phase transition we have temperature over here, but here temperature is replaced by the system size, 1 over the system size. And what you see is the fan. So this is this usual quantum critical fan, and one goes from thermal to MBL, but then for small system sizes, we are up there. Yeah, and the idea is that what we see all of this physics is the critical physics or close to the critical physics, which is not really localized yet. Okay, so and that's the reason why you see some kind of a dynamics over there and so on and so forth. However, one should also monitor the following things. So we have a system size of the order 12, or in my case of the order 20 or so, and the growth that you see is of the order 1. Yeah, so 10 to the power 0 is 1. So it's far smaller than the length of the system size. So the why there is still a finite size effect is I would say is still a mystery, because the delta x is much smaller than the total length of the system size. But still, we believe that, or at least in this work, that has been showed that there may be an effect of finite system size. Okay. How it compares with the localization length of which? Yes, yes, yeah. Oh, I'm sorry. Yeah. Yes. 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 So the point is that for all this disordered strain, the localization length is of the order of 1 lattice spacing. So we are all safe in that, at least the non-interacting localization length. Good. So what I want to emphasize that already the MBL phase itself is very interesting in a sense that there are some sort of a slow transport, which we also saw in terms of entanglement entropy as well, that there is a logarithmic growth of entanglement entropy and volume law. So that even more. Yeah, yeah, yeah. So it even goes further. Yeah, I don't know. So this is precisely that's my point, that this may not be the full picture. So why there is a finite size effects even in the MBL phase for such a big system, and the growth is not that is I would say is not settled. Let's put it in. Good. So what I want to put it now is that this MBL phase is kind of the usual MBL phase where whether it's a cosine potential or a random potential, it shows similar behavior which we saw in this work. But now I want to include symmetries in the problem, and I want to show that even symmetries give even more interesting physics. So for instance, one of the things that one can start with is an SU2 symmetric model, so which is a model which is a spinful Hubbard model. And now we have spin, and then there is this T sigma which is equal for T up and T down. And whenever it is 1, it is just SU2 symmetric, where interaction is taken in the SU2 symmetric point. And in this model already there are very interesting physics appears in the MBL phase. So for instance, what happens is that the spin dynamics, so there are spin and the charge. So the charge is localized, and that is what even in all experiment has been shown, particularly in the cold atom experiments. But the spin dynamics is subdiffusive. This is precisely what has been shown. So T down is taken 1, so 1 is the symmetric point. And what you see is that again, what is plotted is the return probability of the spin density as a function of time, and you see in a log-log plot it goes down. So eventually it just decays down very slowly, but eventually it decays down. So the spin is kind of delocalized, but the charge is localized. And as soon as you break the symmetry, so you go to 0.99, so you break a very small symmetry, and you start to see that this thing goes up. Other way of saying is the system starts to become localized. Okay? So at least the spin degrees of freedom. Now, also if you look at the entanglement entropy itself, in this type of system, what you see is not an area law, which is what one would expect in the case of usual MBL, but one start to see a logarithmic corrections to it. So this is not fully an area law MBL system. Okay, what is that? The overall physics? So the overall physics is the following, that one believes that eventually, because the spin degrees of freedom is delocalized, the charge will feel the spin as a bath. Yeah, and eventually the charge will also delocalize. So currently what one believes that in an SU2 symmetric system, eventually there will be a thermalization, but this thermalization will be anomalous. So it will be not a quick thermalization or anything, it will be a very slow thermalization. Okay, so that's kind of a SU2 symmetric system. What I would like to focus in the rest of my talk is a system where that's why I did not write it carefully, so I don't recall it from my hand, but my head, but yeah, it's done properly, and yeah. Okay, what I will be mostly focusing on is a situation where the disorder is taken in a different position in some sense. So right now, whatever we are talking about, the disorder was one side, but now I will be focusing on a system where we have disorder in the bond. Okay, so this is a bond disorder system, and this system falls into a class of what is in technically called BD1 symmetry, but let me go through what it means. So we have a real hopping, so Ji is real. And as of now, this is just an XY system, which is just a free fermion. No? So if you do a Jordan-Wigner, you will get a free fermion system with a bond disorder. So there is no interaction whatsoever. But already the non-interacting system shows very interesting physics. For instance, so we see that this model is time reversal symmetric. So tau is essentially the time reversal operator. It has particle hole symmetry, where particle hole symmetric operator is constructed out of tau and tau z, where this tau z is essentially a sublattice symmetry. So the model also inherits sublattice symmetry. So this tau z is acted on the sublattice space, and essentially it just means that the CH has this minus H thing. Other way of saying that this model has a particle hole symmetry. Yeah? So there are many consequences of that. So for instance, what we know that the density of states of this model has a logarithmic divergence close to the zero energy, which is not the case for an on-site disorder model. So that's important. So that divergence is very going to be critical when I add disorder interaction into the system. So this is essentially known as Dyson singularity. The next thing is that the zero energy states are quasi-localized. Other way of saying that when I talked about Anderson localization, all the states were exponentially localized. That's how I started out with. But here, these are not the case. So the zero energy states has a localization length which is fluctuating and of the order of square root of the system size itself. So what it means that the system is not completely localized, but there are certain states which are very many because there is a divergence, which are almost of the order of system size. And that's going to play a role in when I put interaction into the system. And at higher energy density, so there are real space RG calculations, excited state RG calculation by Vosk and Altman and Wang and Moore, which shows that the entanglement growth in this model has a log-log behavior, which is again quite contradictory compared to the Anderson model, because again Anderson model will show no entanglement propagation, but already in the non-interacting model for this particular case, we will see log-log propagation. Okay, so that's kind of all of this kind of well understood. So what I'm going to talk about is now I add a ZZ interaction such that I preserve the particle hole symmetry all the time, and then I ask again the similar type of question what has been asked for the on-site disorder, that whether MBL is there, not there, and so on and so forth. Good. To begin with, let me show the usual indicator. So the first indicator is essentially what I call level spacing statistics. This tells you whether there is a difference between a Wigner-Dyson, which is the chaotic, to a Poisson, which is essentially the localized phase. And this has some definition, but eventually there are two numbers that are important. One number is essentially 0.53 and another is 0.39, close to that. And if the energy levels has these two numbers, we can clearly say that, okay, one obeys Wigner-Dyson, one obeys Poisson statistics. And indeed, that's what you see here also. So as a function of disorder strength, measured in the unit of hopping again, we see that as we increase the system size, let's take the largest system size, we can do 20, we do go from the Wigner-Dyson statistics to the Poisson statistics. And in this sense, I will say that this system also shows localization, or at least difference between chaotic regime and the localized phase. But there is a little bit of a thing that one should notice in all finite size numerics is the following, that there is a flow in the system size. As I increase the system size, it seems all the systems or all the curves are moving towards right. Yeah, and this is again a feature that you also see in the random case, but not been analyzed so far. But feeling is that there is no single crossing. The crossing itself for individual curves are moving towards higher and higher disorder, and that can be a bit of problematic things, which I'll tell later actually. Okay, you can look at also eigenstate entanglement entropy. So this is the entanglement entropy bipartite as a function of disorder. Again, it shows volume law over there and kind of an area law, but like the SU2 symmetric system, here also it's not completely area law. There are corrections to it, and we could not fit it to a log because we do not have that many system size, but seems there can be a logarithmic correction as well. So this is an interesting way to look at this data again. So this is the same data, but now we plot it divided by the page value. So the page value is essentially the ergodic value of the entanglement entropy that it can maximally have for a bipartite situation if the system is ergodic. So this is divided by that, and then plotted as a function of system size. And what you see that there is a turning around of this curve. What it means is the following. So, and all of these are different disorders. So let's say I take disorder 1.5. So initially it goes down, means that it does not reach the page value. It becomes much smaller than the page value, or seems like over there. And eventually it realizes that I am not in the localized phase, so I need to turn back. So larger and larger system size, it turns back and becomes more like a volume law. So this is how one should interpret this plot. So it goes down, but eventually when it reaches the correlation volume of the system, it turns back. And that's kind of a tendency even for a very large disorder, which again, due to the finite size systems, we cannot resolve it, but there seems to be a concept of a correlation volume, which one needs to go beyond finite size to see really what is the thermodynamic physics that we are after. Okay, so that's the first part of it. The second part is essentially the entanglement growth. So in this system, again, imagine if I sit in the localized phase, I would have expected that the system will have a log growth of entanglement, but the similar experiment is done here, and what we see, this is not only linear log plot, but a log-log plot, and there is a power law behavior. And that's the first difference from a usual MBL phase, that this is an algebraic propagation of correlation as well as entanglement that we see. So this is a large disorder, and what you see again, both the cases, even for very large disorder. So this is in the unit of exponential, so it's exponential minus WW. We have power law propagation of entanglement. And also at the same time, the volume, so the volume law that we saw in the case of usual MBL is not there. There is again a log correction that we see here for the saturation entanglement. That's the kind of a basic difference between a usual MBL and this one. Eventually, you can also look at the particle propagation that I already mentioned, and you see that, okay, so these are again different system sizes. So we have time is limited because larger system size, you cannot go to larger time. But eventually also what we see is that there is no saturation as of now, what we see. So we see that the particles are also propagating in this context. So again, this is return probability, it also goes down and so on and so forth. Good. So this is kind of the observation that we notice, and I would like to tell you at least qualitatively what we think about it. So the way to think about it is the following. So we start with this following Hamiltonian. So this is written in the Anderson basis. So disorder has been taken care of. So this is all a single particle, diagonal form, and then you add interaction. So these are the 4 fermion interaction that you have added, and this B, M, and PQ is essentially the matrix elements, which is again constructed out of the single particle orbitals. Now, particle Hall symmetry has this important consequence. The first consequence is that the energy comes in pairs. So there is always a positive energy and the negative energy due to the symmetry of the problem. But also that gives rise to symmetry in the wave function. And the symmetry in the wave functions is the following, that these two energies has same center of localization. Okay, so in the Anderson problem, that's not the case. Even if there are energies which are close by, they can have very different places where they can stay. Yeah, but in this particular case, they are staying exactly on the same point. And that is a consequence of the particle Hall symmetry. What it means is the following. So let's start with a state which is a E equal to 0 state, or energy equal to 0 state in the non-interacting case. Again, remember this exactly at energy 0, there is a diverging energy density. So there are many states that you will find close to 0 energy. You can construct such a state in this language by operating from in the vacuum F minus k and k. So that's my 0 energy state. And what it implies in the real space, that they are closely bound together. Okay, and that comes precisely from this consideration that the particles have same center of localization. Yeah. Yes.
Here it's a hopping.
It's a hopping disorder. It's a pure hopping disorder. Yes. Yes. That's all brings all of this. Yes. And what you can do, you can essentially construct this type of states and consider all in E equal to 0 subspace. So let's go to the E equal to 0 subspace just to see what's happening there. And what you can construct an effective Hamiltonian doing simple perturbation theory, first order essentially, because energy equal to 0, the first term drops out, and then there are these terms, but not all matrix element will survive, because I just want to consider these kind of states. And what you see is kind of a fermion type of thing, which is kind of giving you some kind of a dynamics to these bound states. Okay, and this is what I'm going to show you in numerics. So I will project my Hamiltonian in this 2 particle bound state. So I will just consider 2 particles and start with this state, and I would monitor what happens to these states in the non-interacting settings where you have interaction on the nearest neighbor. And this is what has been plotted. So this is sigma plus is the center of mass, and this is the difference of mass of coordinate. And what you see that in this two particle subspace, we have a growth in this center of mass, whereas there is no growth between the distance of the particle. Other way of saying that we are having a hopping mechanism, which is bound state hopping in this model, which is favorable because there is a large density of states of particles. And through this bound state hopping, there is some kind of a transport or entanglement growth that we see in the MBL context. Good. So that's what I wanted to tell you. So I would like to thank my collaborator, Ferdinand, Giuseppe, Felix, and Marcus. The main work is done by Giuseppe, who now recently moved from Munich to Cambridge. So these are the funding agency. And I would like to finish with this picture that I already mentioned. So I have a 1D system. In this 1D system, the bonded disorder. In this bond disorder case, we are having this kind of states which are favorable because these are the E equal to 0 states. And between this, there can be a distance between two of these states, which can be of the order of the localization length. This is again comes from the non-interacting picture. And the matrix element or this BPP that I already showed you is of the order 1. That also one can show, a little bit of calculation can show you that this is of the order 1, which gives rise to a finite overlap between these type of states, and that allow you to hop through the system even if the system is traditionally, we'll call localized. With this, I would like to thank you for your attention.
Thank you, Shomo. Questions?
So I think with the particle hole, briefly touched on this. Okay, okay. But the 2 points, you have this Dyson singularity, and then also in the random matrix, the BD1, that's all.
BD1, yeah.
So exactly how does that come into your analysis with MBL growth and all that? I seem to have missed that point.
You mean?
The fact that you have this 1 over log.
Right. So the way it comes is the following. So precisely this quantity. So what you can show that the fact that there is a particle hole symmetry gives rise to symmetry in the wave functions itself of those two energies. And those two energy leaves even though they have the same center of localization. That's the only thing that comes into the picture. I agree that these are all single particle pictures. So it's not what happens in the presence of interaction. But what I'm trying to say is that these are so many states that even interaction, so you can see the density of state also, it doesn't change much. It shifts the singularity, but not completely remove it in the presence of interaction.
But I suppose there must be some profound effect because you just have proliferation.
Right.
And you also have
Right.
see any evidence of?
Oh, the evidence is precisely the fact that entanglement has this kind of thing, and the particle separation grows and things like that.
Coming from that.
That's the manifestation of that thing.
Exciton delocalization imply that there could be some exciton condensation, spontaneously produced and gain energy by delocalization. That's interesting from experimental point.
Right.
We could discuss it.
Yeah, right. I agree.
Just a clarification, the interaction you put in, it was not particle hole symmetric.
It is particle hole symmetric.
Okay.
It is important.
What was it? Can you just show me that?
In the fermion language, it is just density, Ni minus half, Ni plus 1 minus half. If you break, this half is important. If you do not have that half, you will see the usual localization. It's important. Yes.
Somehow keep
Right.
and charge degree by any sort.
Right.
So eventually back to this.
Right. Right. That's the idea.
Then what is the way about this? I mean, you're talking about something which is at high energy.
Right.
Sort of notion of spin charge separation. Okay.
No.
What is it that? How should one think about this section of this hence localization?
So again, one needs to go back to this resonance picture. Actually, there are resonance that proliferates. If you do a RG calculation, this SDRG, you can show that the number of resonance grows very.
resonance in sectors
Spin
is
sectors.
different from that in the
Exactly. You can be.
There's one more. And presumably it doesn't have any fact that when you don't have disorder, you actually have had hopping terms or something.
No. Yeah.
Yeah. So in this case, I mean, you will have this random singlet, right? So, but somehow you are taking only the nearest neighbor in this picture. So, what about? I mean, yeah.
So this is a first order approximation. So if you take into account the random singlet, which is the non-interacting the ground state, I believe more terms will appear, and it will even more delocalize this. That's my understanding.
So the Dyson kind of singularity which you talked about, so there is a specific exponent which is purely determined by the class.
Absolutely, these three.
So here with I guess the disorder hopping shouldn't change that, but would the interaction do something with that?
So you were asking that what happens to the density of states? So obviously it's
the exponents which is purely determined by the classes.
So the density of states that I mentioned is a single particle density of states in the non-interacting case. Now you are talking about many body density of states, right? So that does not have that particular singularity. It shifts the singularity, but there is no such strong divergence because interaction broadens it out. So it's a many body states. Usually it almost looks like a Gaussian. And
you showed a phase diagram which was with the Anderson localization and
yes.
many-body localization,
yes.
like a quantum phase transition.
Right. So it's not my phase diagram, it's the
Yeah,
experiment.
so how that phase diagram, that was drawn for?
This one, you mean?
Yeah, that's for on-site disorder.
This is on-site disorder, but the disorder is not completely random. It's a quasi-random disorder.
So how this phase diagram will get in your?
In my version means in the particle hole symmetric case. My feeling is that there is no MBL in the particle hole symmetric case.
Good questions? If not, let's thank Shomo.